Frame analysis. Video 17. Concrete design according to second order theory, part 1. We have now performed the design of the frame according to first order theory with regard to both the stiffness method and the curvature method, and reached an acceptable solution. We will now check this with regard to second order theory. To perform a design according to second order theory, we activate this calculation before the analysis and select Calculate. The calculation is, as mentioned earlier, made iteratively, and it is a very sophisticated non-linear calculation performed where the program constantly detects how the cracking in each section changes, and this together with creep and possible shrinkage means that it often takes a while, as in this case, before the calculation is complete. We then again choose program part design. As emphasized previously concerning steel, is the important difference with the calculation according to first order theory that in this case no buckling length in the frame plane is required, as the buckling check now lies in the growth of the second order moments. We make a calculation and can now see that both columns are colored red, and a look in the utilization table shows that these members are overutilized by about 36%. In the code check window for member 1, we see that the checks in the frame plane is made with regard to EN586, meaning the general method, and out of the frame plane with regard to EN587, meaning the stiffness method. We see that it is flexural backing in the stiff direction in the frame plane, a check now made with both positive and negative second order moments that exceeds the capacity. Then follows a check regarding flexural backing out of the frame plane, a check with respect to biaxial capacity, and a shear check, which all are okay. Finally, for the SLS load cases, the crack width is checked, and the allowed compressive stress which remains within permissible limits in this case. If we go back to the program part results and studies the moment distribution for member 1, we see that the moment increases from about 576 kilonewton meter to about 890 kilonewton meter due to second order effects, and it is this moment that is used in the check for flexural buckling in the frame plane. We can now look at how the cracking affects the stiffness. We perform a new analysis and deactivate the option Crack Section Analysis. If we study the moment distribution for member 1, we see that the second order moment now is about 739 kilonewton meter, and the new design shows that the utilization decreases from the previous 136% to about 120%, thus about 16%. In other cases, the difference may be even bigger, so the impact of cracking is important, especially when designing according to second order theory.